Valence bond theory. The other word is hybridization. This is the part of learning of that question in which we are doing VSEPR, Lewis dots structures, will identify sigma and pi bonds. So this big question, which I was telling you that we'll start this doing this question very soon. In this question, one of the part is that identify the hybridization. This one. So I'm teaching you this particular part. And after learning hybridization, you will understand sigma and pi bonds. Then you can answer this also. These things we have done. So let's start with the hybridization. So it's a new topic, children. Hybridization of orbitals. The word hybridization means mixing. Mixing of orbitals. You know different types of orbitals? Yes, Anish, what are the orbitals? S orbital, p orbital, d orbital. Yes, very good. F orbital. You know their shapes? S is spherical like this. P is like a tumble. D, double tumble, double. F, triple. So all these shapes also we did. Now let's see the Lewis dot structure of CH4. Central element is carbon. If you write the electron configuration of carbon, it is 1s2, 2s2, 2p2. Now let's pay attention to the valence shell. Then the valence shell 2s, 2, this one. And in the p subshell, we have 3 orbitals, right? And these 2 electrons are present according to Hund's rule, unpaired. This is called as ground state. Ground state of carbon. Do you think carbon can make 4 bonds with this ground state? So what will happen, Siddharth? So one of the, not expand, because there is one empty. See here, this empty. This is 2p, children. Px, py, pz. So one electron jumps from here, right? One electron jumps from here to here. Then how many unpaired when electron jumps? 4. And then if it has 4 unpaired, then it can make 4 bonds to complete the octet. Now it can make 4 bonds. But do you remember px, py, pz? They are on 3 axes. X-axis, y-axis, and z-axis, like this. Px, see px on the x-axis, like this. This is px. Py on the y-axis, like this. Pz on the z-axis, like this. So what is the angle between px, py, pz? Angle, Veer. Angle in px, py, pz. We look at the corner of your room. Corner of your room, Veer. This is x-axis. This is y-axis. This is z-axis. This is the corner of the room. What's the angle? 90 degree. They are perpendicular. Very good, Anish. So they all are 90 degree to each other, right? Okay. Now, when the bonding is taking place, now let's say hydrogen, this hydrogen. Hydrogen is 1s1. Now, this hydrogen is approaching. Four hydrogens are approaching. All these are hydrogens with one electron. 1s1, 1s1, 1s1. They are approaching and they are overlapping like this. What is the angle you are expecting in CH4? What should be the angle between all these four hydrogens when they make the bonds? Don't you think that they should be 90 degree? It should be 90 degree, isn't it? So CH4 must have a 90 degree angle. Molecule CH4 must have a 90 degree angle. Now let's try to understand this. I'm going to erase this. I hope this is clear. Ground state and excited state. This is ground state. Then one electron jumps and then carbon becomes excited. Now this is excited state. Then the angle expected in CH4 is 90 degree because the p orbitals which are involved, they are 90 degree to each other. Okay. Now let's draw the Lewis-Strauss structure of CH4. Central atom, carbon, make the skeleton, four hydrogens. Follow the rules of Lewis-Strauss structures. How many total valence electrons? 8. How many are used? How many are left, Sanjeev? All are used. So it means nothing is left. So we are done. How many groups around carbon? You remember groups, lone pair and atom. For the four, what is the EPA? Tetrahedral. And what's the angle? Angle of a tetrahedral? Anish? Just take a print out of the notes which I have given you. Just open it and check from there. 109.5 degree. Real angle is this. This is the real structure. This is not the structure. Not this one. Not 90 degree. This is wrong. This is right. But how come the angle is 90 degree when the orbitals which are involved are px, py, pz, and s orbital? How come they are 90 degree? Sorry, how come the angle is 109.5 degree, not 90 degree? They should be 90 degree to each other. So theoretically, I'm getting this. Theoretically, when I'm doing on the paper, looking at the excited state of carbon, and okay, oh, okay, that the angle should be 90 degree when I'm visualizing it. But experimentally, it is like this. This is the real structure, experimental. So it means there is some error in our analysis. And for that, they started using hybridization concept to explain why the angle is 109.5 degree. We are using a concept of hybridization. So ready to understand hybridization? Okay. So what is hybridization, children? Mixing of orbitals. Mixing. of orbitals. Simple language, mixing of orbitals. Let's see how the orbitals will mixed. We understand this. Just like you make a soup. If I give you tomatoes, potatoes, so many vegetables, and if I ask you to make a soup uh, with uniform consistency, you will boil all of them and you will churn them and then make a smooth paste, right? Same here. You mix all the orbitals and make a paste. If tomatoes are more, the taste of tomato will be more, texture of tomato will be more. If potatoes are more, then the taste of potatoes will be more, texture will be more. Same here. If s orbital is more, if p orbital is more, based on that, they will acquire a particular shape. So we'll understand mixing of orbitals. Let's start with CH4. We know that around carbon we have 4 atoms. It means carbon needs 4 orbitals of exactly same composition, same energy, same shape. Carbon is in need of 4 orbitals of exactly everything same. Okay, let's see how carbon is going to achieve it. So here is carbon. Can you give me the excited state of carbon, children? All of you? Excited state of carbon in terms of S and P. Mhm. Yes, very good. 1 second. Some students have not joined. Okay, very good, Sashank and Sanjeev, Veer, Yug, perfect. So I'm placing it like this. This is 1s2, and this one is 2s1. This is 2p3. Means every orbital has one unpaired electron. Hund's rule, children, Hund's rule. Okay, now which orbitals will participate in bonding? Which orbitals will participate in bonding? Only the outermost shell. Say like this, 2s and 2p, the way Sanjeev has said. This one. How many are these? 1, 2, 3, 4. How many you are in need for making these bonds? 4. Mix them. You are mixing 1s with 3p orbitals. This is 1 and this is 3. You're mixing them. After mixing, you will be getting sp3 hybridization. And these 4 orbitals will become now exactly same in size and energy after mixing. Mixing. I'm getting 4 orbitals. 1, 2, 3, 4. And each orbital has one electron, like this. Because I'm mixing one s with three p's, this hybridization is called as sp3. And the name of the orbital is not s or p. Now this is sp3 orbital. sp3, 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 sp3. The shape is not like s or p. The shape of sp3 orbital will be around a tetrahedron. 4 means tetrahedron, like this. This is sp3. This is the shape now. This is sp3. This is sp3. And this one is sp3. So shape of the sp3 orbital is like this. This is one of the sp3 orbital, sp3. And there are four of them. 1, 2, 3, 4. So put them on a tetrahedron. Make this line like this. Like this. And then now your hydrogen will come. Hydrogen is 1s1, 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 1s1. It will start overlapping like this. This is hydrogen. This is hydrogen. This is hydrogen. This is hydrogen. See, 1s, because this one is not undergoing hybridization. It's pure 1s orbital. So now they will overlap to make chemical bond. This is the overlapping. Now, this is the axis of the sp3 orbital. This 1s of the hydrogen and sp3 of the carbon are overlapping on the axis. Real overlapping of the orbital. You can see that they are sharing space like this. This is called as sigma bond. Sigma. What is a sigma bond? Which is formed by, it's very strong. And it is formed by overlapping on the axis. Formed by overlapping of the orbitals on the axis. On the axis. Are we okay with this? Yeah, please. Any questions? So what is sp3 hybridization? Anyone? No, when sp2 mixes with another shell means? No, I'm not getting your question, Siddharth, and I'm not getting Sanjeev what you are saying. We're talking about sp3. In sp3, how many orbitals you are mixing? You're mixing one s with three p's? You're not getting sp2, you're getting sp3. sp3 is the mixing of one s with three p's. sp3 will give you four orbitals. Because you're mixing four, you will get four. Here, I'm mixing these four. I'm getting four. The name is sp3. Four will be around the tetrahedral. So that's why I made a tetrahedral here. This tetrahedral. Is it okay? Siddharth, your question, Sanjeev, is okay. Siddharth, your question is answered. sp3 is a type of hybridization in which you are mixing one s with three p's. sp3 is always for 4, means for tetrahedral. Whenever you see a tetrahedral carbon, tetrahedral atom, you will say, oh, it is sp3 hybridized, right? Okay, 1 second. Yeah. Children, if you are leaving the class, yeah, I'm better. I'm better. Then you must let me know that you're leaving the class, okay? Thank you very much, Veer. I'm slightly better, better than yesterday. Today I have plenty of medicines next to me. Okay, great. Understood sp3, right? Now making another picture. Let me show you sp3 hybridized atomic orbitals. Let's say ammonia. Draw the Lewis dot structure. Yeah, Sanvi, I was searching you on WhatsApp. Okay, that's good. You missed sp3, so I'm doing it again with another example. We did one example already. Now draw the Lewis dot structure. N central atom, 3 bonds with hydrogen. Any lone pair on the nitrogen? Total valence electrons. So, yes, Yuk. Yes, there is one lone pair, right? Okay, so how many groups are on nitrogen? So what hybridization is needed on nitrogen? sp3. Nitrogen will undergo sp3 because there are 4 groups. 4 groups needs 4 orbitals. Orbitals are like rooms. So this nitrogen is in need of 4 rooms so that it can have 3 bond pairs and 1 lone pair around it. Let's see how the mixing of orbital will take place. This is nitrogen. 1s2, 2s2, 2p3. Outermost shell, this one. Let's make outermost shell. Now you mix them. You mix all of them because you need 4. So you have to mix this 2s with these 2p's. Mixing. After mixing, I'm getting how many orbitals, children? After mixing, how many orbitals I'm getting? 4. 1, 2, 3, 4. Now these 2 are paired already. These 3 are. Yes, Veer, you can. Don't wait for my permission, Veer. You just inform me and then come back as early as possible, okay? Don't miss the concepts. Now what is this? sp3 orbitals. How many of sp3 orbitals? 4. It will be arranged around a tetrahedron. One sp3 orbital is this. Other sp3 orbital is this. Make these pictures in your notebook. Third is this. And fourth is this. One of the sp3 orbital is holding the lone pairs. The lone pair. These are the lone pairs. Lone pair. Other three sp3 orbitals are overlapping with the hydrogen. Hydrogen 1s1, 1s1. There are three hydrogen you can see. So they are overlapping like this, like this, like this. So let's put hydrogen here. Hydrogen. Here is the bond pair. This is the bond pair. Hydrogen. This is the bond pair. Hydrogen. This is the bond pair. What kind of bonding is this? This one. What kind of bonding? It is sigma bond. Represented by sigma like this. Sigma bond. This is sigma bond. How many sigma bonds are there in NH3? How many sigma? 3 sigma bonds. So remember, two atoms always make a sigma bond first. Make a sigma bond first. And they can make only one sigma bond. Like this nitrogen and this hydrogen can make only one sigma bond. Not more than one. Two atoms, these two. Nitrogen, hydrogen, only one. Because they can have on the axis overlapping only once. So one is sigma bond. Now I'm going to teach you about the second type of hybridization. We call it as sp2 hybridization. Ready for it? Let's take this example. C2H4. Carbon is bonded to carbon. So let's make the Lewis dot structure. Like this. Skeleton. Now, how many total valence electrons? 12. 2 carbons, 2 times 4 plus 4. 12. Hydrogens are already done. They can make only one bond. Carbon can make maximum how many bonds? Carbon can make maximum 4. So what should I do here? Make a double bond. Yes. So there is a double bond, right? Okay, now look, count the groups on this carbon. Count the groups. How many groups are there on the red carbon? How many groups? Groups are the atoms and lone pairs. So on the red carbon, how many atoms are there? 3. 3 groups are there. And on this carbon, how many groups? 3. So during hybridization, I need only 3 orbitals. So now let's see the excited state of carbon. It is excited state is 1s2, 2s1, 2p3. This is the outermost shell. Now, how many orbitals you are in need? Check your requirement. Your requirement is of 3. So, how many you will mix? You will mix 3 only. Like if you're making soup, then you're making soup according to the requirement. If you require for 3 people, then you'll make only for 3. Same here. These orbitals, they will mix according to the requirement. Now they will mix 3. If you are mixing 3, how many you are getting? Mixing 3 will give you 3. And what is the name of these orbitals? You are mixing 1s with 2p's. What is the name? sp2. sp2. 1s with 2p's. I'm getting 3 sp2 orbitals. Each orbital has 1 electron. And what about this one? Pure p is left as such. These are actually pure orbitals. Before hybridization, we call them as pure orbitals. After hybridization, we call them as hybrid orbitals. Hybrid orbitals. So this pure orbital is always, these are pure orbitals are higher in energy. They are higher in energy. So these pure orbitals, this is pure p. This one is pure p orbital. It didn't participate in hybridization and it's left as such. Now, can you see the state of the carbon? The red carbon? It has 3 sp2 orbital and 1 pure orbital. sp2 orbital is on a trigonal planar because there are 3. 3 means trigonal planar. So these orbitals are arranged like this. This is one sp2 orbital. This is another sp2 orbital. And this is third. Trigonal planar. Is it clear, children? But where is this pure P? Where it is? It is standing perpendicular to the trigonal planar like this. This is pure P like a dumbbell like this. Pure P. See, these are sp2 orbitals, this one, and this is pure P. Your carbon is like this. This red carbon is like this. Let's make it here. I'm making the red carbon here in the orbital picture. It is sp2 because it has 3 groups on it. So this is the red carbon. It is trigonal planar. 3 groups means trigonal planar like this. This is one of the sp2 orbital. This is another sp2 orbital. This is third sp2 orbital. And it has one pure p orbital standing perpendicular like this. Electrons are present. Is it clear, children? Picture is clear, orbital picture. Now, where are the hydrogens? Here on these two. Hydrogen, hydrogen. These are sigma bonds. These are sigma bonds, right? Now, this carbon is sp2. What about this carbon? The nature of this carbon. What is the nature of this carbon? Check the groups. How many groups on this carbon? Count the groups, children. So it is also sp2. Exactly same. It is also sp2. So let's make it this carbon over here. It's also sp2. So it has one sp2 orbital like this. Other sp2 orbital here. Only trigonal planar. See, trigonal planar. Trigonal planar. And then you have a hydrogen here. And then you have a hydrogen here. This is hydrogen. This is hydrogen. And then these are the electrons of the hydrogen and carbon sharing. This is carbon here in the center. Then there is one p orbital like this. Like this. Pure p. Now this pure p orbital cannot have on the axis overlapping. You can see that. So what kind of overlapping is there? Sideways. The overlapping will be like this. Sideways. Very good, Anish. Sideways overlapping. Sideways overlapping means pi bond. This is not sigma. This is pi. Can you see the difference in sigma and pi? Sigma is on the axis overlapping. Pi is sideways overlapping. This is sigma. This one is sigma. And this one is sigma. And this one is sigma. So sigma bonds and pi bond. Which one is stronger bond? Which one has more stronger overlapping? Sigma bond or pi bond? Which one is sigma? Which bond is more stronger, sigma bond or pi bond? Am I audible, children? Hello? Yeah, sigma is more stronger. Sanjeev, you're right. Because it's the real overlapping. You can see that how the real overlapping is taking place. They are sharing the space like this. Sigma bond is very strong. And pi bond is sideways overlapping. Like two cars, they are undergoing head-on collision. Means they are one car is here coming from this direction, other car is coming from this direction like this. This is head-on collision, very strong. But if one car is going like this and other car is just touching it from the side, this kind of accident. This accident is not so severe because this overlapping is not so effective. So exactly in the same way, the sideways overlapping is not very effective, it's weaker. But on the axis overlapping is very strong. So sigma bonds are stronger than pi bonds. Please write on this. Sigma bonds are stronger than pi bonds. Are we clear about it? This picture is clear, children. This carbon is sp2. This carbon is also sp2. So sp2 means trigonal planar. This molecule is trigonal planar. It has 1, 2, 3, 4, 5. 5 sigma bonds. And 1 pi bond. Pi. Like this. You can put it like this, or you can say pi pi. This one. We are clear? Sashank, any question? Yuk? Okay. Ready for another hybridization? Okay, before we go for another hybridization, let's have a review of sp2 and sp3. What kind of hybridization is there in bf3? Question is, what kind of hybridization? So draw the Lewis dot structure. E, the central atom. Make the skeleton. Complete the octet of the fluorine. Check total valence electrons. Check how many are used, how many are left. Is there any lone pair on B? Yes, none. Very good. Now around B, how many groups are there? 3 means trigonal planar, right? For 3, what hybridization is needed? You need 3 orbitals. For 3, what hybridization is good? sp2. Boron is sp2. You can see the electron configuration of boron. 1s2, 2s2, 2p1. This is the ground state. In ground state, I have only one unpaired electron. With that, I cannot do anything. So what happens? One electron jumps from 2s to 2p. Now you can see 3 unpaired electrons, the excited state of boron. 3 unpaired, right? Now you are going to mix them together. You are mixing 3. You are getting 3 hybrid orbitals which are lesser in energy than pure orbitals, more stable. You are getting 3 after mixing. This is pure p orbital which is left empty, nothing there, empty. Now these 3 sp2 orbitals will arrange themselves around boron on a trigonal planar with an angle of 120 degree. One here, one here, and one here. Then they will overlap with the p orbital of the fluorine. You know, p fluorine electron configuration 1s2, 2s2, 2p5. Look at the outermost shell. It has only one unpaired electron. This one. This is the one which is going to overlap with the sp2 orbital of the boron. This is p orbital. So the shape will be like this. Like this. Like this. Overlapping on the axis. Overlapping on the axis. These are the bond pairs here. How many sigma bonds around boron? Yugi is saying 1. And he's very wrong, children. How come 1 sigma? So how many then? Only Yugi is answering. Where are you? Shashank, Siddharth, Sanjeev, Veer, Anish. Anish, you're back? Yeah, you were back. Yeah. This is sigma. This is, yeah, 3. There are 3 sigma bonds. Is there any pi bond here? No, there is no pi bond. Ready for another example? Okay, we are going to make the Lewis dot structure of SO4 2 minus. Sorry. Central element, sulfur. There are 4 oxygens. Skeleton. Total valence electrons, 32. Complete the octet of the oxygen. How many oxygens are singly bonded? And how many oxygens are doubly bonded? Yeah, 2 oxygens are singly bonded and they will be holding this negative charge with 3 lone pairs like this. All these things we have done earlier, right? And 2 of the oxygen will be doubly bonded. Can you check how many groups around sulfur? Groups around sulfur. So what is the EPA for sulfur? Is tetrahedral. What's the hybridization needed? The hybridization, because there are 4 groups, I need 4 orbitals. So a sulfur will undergo sp3 hybridization. How many sigma bonds? Every atom is going to make one sigma bond first. Means this is a sigma bond, this is a sigma bond, this is a sigma bond, this is a sigma bond. 4 sigma bonds. How many pi bonds? Whatever double bonds are there, these are pi bonds. Veer, where are you? Veer, please answer. Pi bond. There are 2 pi bonds. Okay. Okay, Veer. You can show me your angry face. Okay. Whenever I say, okay, answer here, where are you? Don't worry. We'll keep fighting like this till the end. So there are 2 pi and 4 sigma bonds. This is how the questions will be answered. Whenever there is a double bond or a triple bond, like C, there is a triple bond like this, N, H. In this case, only one is sigma because I told you that 2 atoms can make only one sigma. Only one is sigma. Other 2 are pi bonds. So let's take the another example where we have to see the different type of hybridization. Look at this carbon. Around this carbon, how many groups are there? How many groups on this carbon? 1, 2. Only 2. So what hybridization is needed? sp. So the third category of hybridization is sp hybridization. This one. Let's take an example. C2H2. Draw the Lewis dot structure. Carbon is chemically bonded to carbon and there is one hydrogen here and one hydrogen here. This is the skeleton. Because hydrogen can never be the central atom. That's why I made it like this. I didn't put any hydrogen in the center because you remember rule number 1. Hydrogen can never be the central atom. Yes, Siddharth, you are right. Now, how many bonds are needed on this carbon? Carbon can make maximum 4 bonds. So what should I do? You make a triple bond on this side. Don't touch hydrogen. Hydrogen is done triple. This time, Siddharth, we are making a triple bond. This hydrogen cannot have multiple bond. So we have the only option that between these two carbon make a triple bond. Everybody is happy. See, everybody. Hydrogen happy, carbon happy. Everybody is happy in this manner. This is a molecule, acetylene. It's a very popular molecule. Very combustible. Yes, Shashank. Okay, now let's see the configuration of hydrogen. Excited state, children. We are working with the excited state because ground state is not going to help us, right? We need the excited state. Carbon is always in the excited state whenever it is bonding. This is the excited state. And this is 2s and this is 2p. 2s1, 2p3. Okay, now check this carbon, blue carbon. How many groups around blue carbon? How many groups? Two. So how many? Two, Anish. Blue carbon, this one. Anish, two. Hydrogen and carbon. Isn't it? Okay. So if you have two groups, then how many orbitals you are going to mix? How many orbitals you are going to mix? Two. Mix them. I'm mixing two. What's the name of the hybridization? sp. I'm mixing two. I'm getting whatever number you are mixing, you will get exactly same number. I'm getting two. And these are left as pure p orbitals. These two. sp orbital is also like this. This is sp, one of the sp. These are two, so it should be linear. Two are 180-degree apart from each other. This is another sp, like this. So this blue carbon, I'm making the blue carbon orbitals here of this carbon. Carbon is here. One sp orbital, another sp orbital. Who is overlapping this side? Hydrogen. Here is the hydrogen bond pair. And what about these two p orbitals? The one here, pure p orbitals. Where are they? They are standing perpendicular on this carbon, like this. Check. One p orbital, children. Another p orbital, like this. These are two p orbitals. Now, let's check this carbon, this one. What's the hybridization needed on this carbon? What's the hybridization? sp, because it has only two groups again. Same situation, exactly same kind of shape. So I'm making here. This is one sp. Can you see sigma bond here? This sigma bond with this carbon. One of the bond is sigma, and this is sp. And here is your hydrogen. This is also sigma, but it also has two p orbitals, pure p orbitals, standing perpendicular to each other, like this. Now these will overlap like this. They are not empty, they are filled. See, one electron in each one of them. So they want to share it. What is this bond which I'm making right now? What type of bond is this? Sideways overlapping. The name of the bond is pi bond. You can write pi, pi, pi bond. This is pi bond. And this one is also pi bond. So how many pi bonds are here? And how many sigma bonds in this molecule? In this molecule, how many pi bonds, how many sigma bonds? Yug has done error. 2 pi bonds are correct, children, but sigma are 3. Let me show you all sigma. 1, 2, 3. 3 sigma bonds. Are we clear about sp hybridization? Sp means two groups, means linear. So your number of groups will tell you the hybridization, number of groups. If groups means lone pairs and atoms around the central atom. If groups are 2, hybridization is, yes, sp. If groups are 3, hybridization is very good, sp2. If groups are 4, hybridization is sp3. Now be careful. If groups are 5, hybridization is mhm. You have only 3 p orbitals. You don't have 4 p orbitals. So you mix one s with 3 p's and add one d. Can you see you are mixing how many orbitals you are mixing? You are mixing 5. One s, 3 p's and one d. So total orbitals I'm mixing are 5. So how many hybrid orbitals I'll get? 5. Is it okay? If groups are 6, then the hybridization is, if you have understood this, you can answer this. I need 6 orbitals. Yes, very good. sp3 d2. When groups are 2, what is the EPA for the 2 groups? Linear. For 3 groups, 3. Trigonal planar. For 4 groups, tetrahedral. For 5 groups, trigonal bipyramidal. For 6 groups, octahedral. Yeah, Siddharth. But more popularly, octahedral. Okay, now, if it is linear, what's the angle? Angle? Linear angle is 180 degree. Trigonal planar angle is here 120 degree. Tetrahedral angle is tetrahedral angle. All of you please type tetrahedral angle. 109.5 degree. And here if you remember, 3 angles were there in trigonal bipyramidal. Anish, I was asking the magnitude of the angle. It is 90 degree, 120 degree, 180 degree. Remember in trigonal bipyramidal, there are two types of bonds. 3 are on a trigonal planar. 2 are standing perpendicular above and below that trigonal planar. What is the name of this bond? It's called as equatorial. We were doing in the last class, last 10-15 minutes, we were discussing this. Remember equatorials? And 2 are Axials. Where would you like to place your lone pairs? On the equatorial or on the axials? Where would you like to place your lone pairs? If you remember, we were discussing that equatorials are 120 degree with each other, and axials they make an angle of 90 degree with three equatorials. It's like you take your paper, your notebook, draw a trigonal planar on it, and put your pencil on the top like this. This is the pencil on the top. So you can see that how this pencil is making in 90-degree angle with these three lines. The pencil is making 90-degree angle with these lines. That's very close, right? So where would you like to place your lone pairs? On the equatorial. Lone pairs are always going on the equatorial for minimum repulsion, right? So this we have to memorize and keep practicing that lone pairs they go on equatorials. Octahedral, what's the angle, children? 90 degree and 180 degree. Two angles are there. So are we clear about hybridization and how to identify hybridization, how to count sigma and pi bonds? Any questions? Okay, what is the full form of this E? Who is going to type? Full form of this E. Very good, Anish. Perfect, Yog. What is the full form of this A? Yes, axial. Yes. Veer, are you busy in something? You didn't answer. A is axial. Can you type Veer? Axial and equatorials. A for axial and E for equatorial. Yes. So that's the complete story. Now we are ready for making Lewis dot structures and answering these questions. See, this is the sigma and pi bonds. Like this is one of the bond is sigma. It's like this, sideways overlap. Exactly same orbital picture I was making. This is one pi bond. You can see here there is one pi bond, but it has two lobes. Two lobes. One above, one below, but counted as one only. In the orbital picture, they are overlapping like this. This is one p orbital. This is another p orbital. I was making it like this. So these are overlapping. So one lobe is this, and one lobe is at the bottom. But actually, it is one pi bond, sigma bond. You can see sigma bond, children. I also made the same molecule BF3, sigma bond. See, triple bond, two pi bonds. One, this is one of it. One lobe, another lobe. Then behind it, there is another, you can see. This is the second. This example also we did. We did all the examples. No questions? So ready for the questions? Let's do it. XEF4. Draw the Lewis dot structure and start answering these questions. Central element. Now my turn is over. I have explained you everything. XE. Skeleton. Do you think fluorine can make a double bond? Fluorine? No. Why? What is the reason that fluorine cannot make a double bond? Anish, what is the reason? No expanded octet. Yeah. And it has only one unpaired electron. It cannot expand the octet, so that is right. But it also has only one unpaired electron. One unpaired is giving only one electron, so it will get only one. It can complete its octet only by one electron. So that's why it's never going to make a double bond. So complete the octet of this fluorine with three lone pairs. These are the lone pairs, children. How many total valence electrons? Very good, Veer. Is it? Veer is right? Yeah, good. 36. How many are used? How many are left? Where they will go? Two lone pairs on the axis. Okay, we have done. Now, total valence electrons, you are going to place here 36. Lone pairs on the central atom, you are going to place here 2. Atoms on the central atom, how many atoms are there on the central atom? See, answer this question. Third, how many atoms? Okay, you are doing some very big error. On the central atom, this is the central atom. How many atoms? 1, 2, 3, 4. Yug, why did you say 1? You must be understanding some in very wrong manner. Is it clear? No, no, no. Atoms on the central atom. So there are 4. Total groups on the central atom? 6. 4 plus 2, 6 lone pairs and the atoms. EPA for the 6. EPA. Octahedral. Bond angle 90° and 180°. Hybridization. You need 6 groups. 6 groups means you need 6 hybrid orbitals. How can you get 6 hybrid orbitals? sp3d2. That's right. Number of pi bonds? Number of pi bonds are 0. Number of sigma bonds? Yes. Formal charge on Xe? Any formal charge? Use that equation to calculate the formal charge. Yes, 0. Formal charge is also 0. The molecular geometry? Yes, Sashank. The molecular geometry is square planar. Square planar, very symmetrical. Is it symmetrical or not symmetrical? Symmetry of the molecule? Yes, it is symmetrical. If it is symmetrical, polarity of the molecule, is it polar, non-polar? Yeah, so non-polar. If it is non-polar, what type of IMF? Only LDFs, yes. Number of electrons around the central atom? Count the electrons around central atom, total electrons, including the lone pair and the bond pair. Yeah, six groups means 12 electrons. Yeah, 12. Can you see? So these type of questions are there on the website. When you click on the quiz, you will get 10 questions, I think. I'll check that how many questions I have placed. But you can do that quiz 10 times and you'll get plenty of new questions because I have made nearly 80, 90 questions. If you feel that there is some error in the question, then flag it. Because when I was making it, maybe I have done some error because I was making in bulk. Ready for another question? Let's make it. Central element, mhm. Central element children. P. Skeleton. Total valence electrons. Mhm. 32, right? Complete the octet of the oxygen. So just think about P. P can make maximum how many bonds? P can make maximum how many? Yes. So do you think oxygen is happy to make a double bond here? Yes, it is. Yeah. Now, two lone pairs on the oxygen. But chlorine will not make a double bond now because it's not the central atom. This also you can write down somewhere. Chlorine, bromine, iodine never makes a double bond just like fluorine if they are not the central atom. Makes a double bond. Please take care if they are not the central atom. If they are the central atom, they can make plenty of double bonds. These are the tricks which can help you in making these structures very fast. Just take care of this. Yes, Anish. But Anish, when they are not the central atom, if they are the central atom, then they can make multiple bonds. Okay, now we are here on the chlorine. Complete the octet like this. P can make only 5 bonds. P is already with 5. That is also telling you that no more double bonds. So how many groups around P? Now answer this question 1. Question 1 is 32. Question 2, answer this. Lone pairs on the central atom. Lone pairs on the central atom. 0. Atoms on the central atom. Total groups on the central atom. EPA for 4. EPA for 4. Tetrahedron. Approximate bond angle. Hybridization. Very good, Siddharth. Number of pi bonds. Very good, Yug. Number of sigma bonds. Very good, Yug. Siddharth. Shashank? Shashank, you are answering questions? No. Shashank, are you there? You're not answering. I hope you are understanding everything. Shashank, you are understanding everything, but you are not answering. Why? Are you busy in doing something else? Then answer. Okay, if you're not doing anything else, then your hand should be in the chat. You should be typing answers here. Formal charge on the central atom? Zero. Use that equation. Molecular geometry? No, 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 Siddharth. If there are four groups and all four are atoms, it's tetrahedral. How come it is square planar? Square planar is only in case of octahedral. So this is tetrahedral. Draw it properly the way I have made. I made it exactly as tetrahedral. How many number of electrons? Shashank is saying 10 and he is correct, very correct. Symmetry of the molecule. Molecule is symmetrical or not symmetrical? Not symmetrical. If it is not symmetrical, then it is polar or non-polar? It is polar. If it is polar, what kind of IMF? You give me DP, the stronger one first, and then LDFs. Yes, very good, Sashank. Perfect answer. Okay, so ready for another? SOCl2. Central element, skeleton, one oxygen and two chlorines like this. Total valence electrons, total valence electrons, children. Sulfur is 6, oxygen is 6, chlorine is 7. So how many total? 26. Very good. Lone pairs on the central atom. Now we have to draw it first. After that, we can answer these questions. So let's complete it. Complete the octet of oxygen. Oxygen will make a, because sulfur can have expanded octet. So oxygen can make a double bond very happily with sulfur. But chlorine will not make a double bond. Agreed? I gave you the rule. How many are used? How many are left? So where these two electrons will go? Rule number 5 in my notes. They will go on the sulfur. So now, so there is one lone pair. Atoms on the central atom? 3. Total groups on the central atom? 4. What should be the EPA? For the 4, what is the EPA? Tetrahedral. But I didn't make it tetrahedral. So let's make it properly. I'm making it properly with sulfur with the lone pair and oxygen, chlorine, chlorine. This is tetrahedral. In the examination, you have to draw it again after deciding everything, because once the molecule is given, you start following the rules and make the structure. At that time, you're not deciding the EPA. Once you decide the EPA, draw it again. Very good, Shashank. Approximate bond angle. Hybridization. Approximate, you will put this, you will get this option only. Hybridization. See, this angle, Shashank, what you are giving me was in ammonia. So we have the only option that's slightly lesser than 109. We cannot memorize so many angles. So here the angle may not be exactly 107. So that's why we are saying approximate. Yeah, children, hybridization. Veer, you are again not answering. No, you didn't answer any. You answered only that number of groups four. That's it. After that, you didn't answer anything. If others are answering, it doesn't mean that now you need not to answer. Whatever I'm asking question, I want answer of every question from you here in the chat. Children, questions are for everyone, not for only one student. Sanjeev, you also please. So hybridization is sp3. Don't just be someone who is just watching that others are answering. No, where is your answer? Give me your answer. Just writing one simple answer and then missing 10 answers is not correct. Number of pi bonds? Yes, one. Number of sigma bonds? Sigma bonds are 3. Formal charge on the central atom? Check the formal charge on the central atom. Remember the equation? Valence electrons minus number of bonds minus 2 times lone pairs. Yug is wrong, Siddharth is right, Veer is right, Shashank is right. Yug, check what error you did. Are you using this equation? 6 valence electrons. There are 4 are used in making bonds 1, 2, 3, 4, and 2 are there as lone pair. 0. So 0. This question was answered by Shashank earlier. So what's the molecular geometry? It's not tetrahedron. It's distorted by lone pair. What is the name of this geometry, children? We were doing it yesterday. No, Siddharth. Check your notes, the notes given by me. There is a trigonal base with a pyramid. Remember trigonal? Yes, trigonal pyramidal. If out of 4, 3 are atom, 1 is lone pair, then is trigonal pyramidal. Number of electrons around the central atom? Shashank is saying 10. Yeah, he's right. Symmetry of the molecule? Not symmetrical, distorted by lone pair. Atoms are also different. Molecule is polar or non-polar? Polar, yes. Type of IMF? Yes, dipole, dipole, and LDFs. Very good. Ready for another? IF3. Central element? Central element, children. Iodine. Make the skeleton with single bonds. Count the total valence electrons. 4 times 7. Yes, Anish, right. Now, complete the octet of the fluorine. How can I complete the octet of the fluorine? Okay, take your time. I think you people are making it in your notebook. Okay, I'm giving you a few minutes. Draw it in your notebook and then we'll start answering my questions. Ready? So now complete the octet of the fluorine. How can I complete the octet of the fluorine? Now please start answering. How many lone pairs, Sanjeev? 3. Check how many are used, how many are left. How many are 4 are left? Yes. Out of 28, 24 used and 4 are left. Where they will go? 2 lone pairs on the iodine. Okay, now answer this. So lone pairs on the central atom? Yes, Veer, very good. Very good, Veer. And lone pairs are 2. Atoms on the central atom? Total groups on the central atom? EPA of the central atom? 5 groups EPA? Electron pair arrangement for the 5. Yes, trigonal bipyramidal. Yes. Approximate bond angle? 90 degree, 120 degree, and 180 degree. You will get this option there. Hybridization, be careful. 5 groups. Mixing of 5 orbitals. I have to mix 5. So, yes, very good. sp3d, just like D, Yug. Okay. Veer, only D. Don't try D1. Just D. No, no, there is no need of saying sorry. Number of pi bonds, number of sigma bonds, formal charge on the central atom. Now let's draw it properly. You are saying this is trigonal bipyramidal. So I'm going to make 3 equatorials and 2 axials. Where would you like to place your lone pair? On the equatorials or on the axials? Answer it. Where should I place these lone pairs? Remember, I was telling you equatorials, axials. Where should? On the equatorials. Very good, Yug. Place them here. And fluorine here. Fluorine here. Now, the lone pairs will not make any bond. There is no bond. They are in the orbitals. In the hybrid sp3d orbitals. Like this. What the shape? What's the molecular geometry, children? Shashank is already answering. T-shaped. Very good, Shashank. T-shaped. I told you to take a printout and keep it next to you till the time your AP is not over. Number of electrons around the central atom? Number of electrons are 10. Very good. The molecule is symmetrical or not symmetrical? It's not symmetrical. If the molecule is not symmetrical, then the molecule is polar or non-polar? It's polar. Oh, you people are faster than me now. Dipole, dipole, and LDFs. Very good. You all are clear about it? All of you have answered your share? Like every question, all of you have placed the answer here? So don't think that, okay, she's asking other question now. I'll just watch that what others are answering. No, everybody has to put their answer. Ready for another? Okay, I'm giving you 2-3 minutes. Draw it in your notebook. Then start answering my questions. Okay, ready? Central element, children. Iodine, skeleton, skeleton. The other atoms are also iodine. Total valence electrons, 22. Complete the octet of this iodine. You know that is not going to make a double bond now. So 3 lone pairs, very good. Check how many are used, how many are left. How many are used, how many are left? So how many lone pairs on the central atom? 3 lone pairs. Now, question number 2, 3 lone pairs. Atoms on the central atom? 2. Total groups on the central atom? 5. Electron pair arrangement? Electron pair? Trigonal bipyramidal. Approximate bond angle? 90 degree, 120 degree, 180 degree, right? Hybridization? sp3d, very good. Number of pi bonds? 0. Number of sigma bonds? Uh, 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 yeah, yes, sorry. Yes, you're right. 2. I was thinking something else then. 2. Very good. Excellent. All of you are right. Former charge on the central atom? Yes, this is -1, children. This iodine is actually using 8 electrons. It has given only 7, but it's using 8. 1, 2, 3, 4, 5, 6, 7, 8. That's why it has -1 charge. Molecular geometry, Sashank is again right. Sashank is doing these answers very nicely. The molecular geometry, linear, yes. Number of electrons around the central atom, 10, very good. Is this molecule symmetrical? Yeah, you're right. This is symmetrical, non-polar, but actually this is ionic. The molecule is symmetrical, but the polarity of the molecule is ionic, is I3 minus. So you're not going to call it a non-polar molecule, right? It's ionic. It's ionic. You will have this option there. Types of IMF. What type of IMF? Ion. That will be there. It's an ionic compound, right? So the dominating attraction is ion. Yeah, they all are there. Yes. You can say ion, dipole, and LDF. Are we clear about it? Okay, this is I3 minus. Why this molecule is symmetrical? Who is going to help me in this? Where would you like to place? You said it's trigonal bipyramidal. So let's make a trigonal bipyramidal. Where should I place my lone pair? I should place my lone pair on the equatorials and the other iodine on the axials to have minimum repulsion. Now this is a trigonal base which is very symmetrical. Trigonal planar, you remember trigonal planar is symmetrical. The sum of all these dipoles must be 0. So this molecule, actually this is ionic, so we need not to worry about the polarity. If somebody is ionic, then it's very polar. So whenever you see that there is a negative or positive charge on the ion, then the polarity of the molecule will be ionic. Ready for another example? XeF2. Let's do it. Total valence electrons, children? 22. Complete the octet of the fluorine. Check how many are used, how many are left. So how many lone pairs on Xe? You have used, out of 22, you have used 16. So 3 lone pairs. So total valence electrons are 22. Lone pairs on the central atom are 3. Atoms on the central atom are, question number 3, 2. Total groups on the central atom are, EPA is, yes Anish, EPA, trigonal, bipyramidal. Approximate bond angle is, your number of questions are missing from Veer. Hybridization is sp3d. Number of pi bonds, 0. Number of sigma bonds, 2. Formal charge on the central atom, 0. Very good. Molecular geometry. Remember 3 lone pairs, they have to be placed on equatorials. Linear. Yes, very good. Number of electrons around the central atom, 10 electrons. Symmetry of the molecule, symmetrical. Polarity of the molecule, non-polar. Type of the IMF, only LDFs. This is not ionic. That's why it is non-polar and LDFs are there, because Xe is trigonal bipyramidal. Lone pairs are only trigonal planar, which is very symmetrical. The sum of all dipoles will cancel out. And these two fluorines are exactly in the opposite direction. They are also canceling out each other like this. So the sum of all dipole is 0. Molecule is non-polar. Yes, children. Are we okay with this? So this is your very important topics are done. Lewis dot structure, valence shell electron pair repulsion theory, VSEPR, valence bond theory. What is valence bond theory? Lewis dot structure. First topic is this. We have done it very nicely. Second, VSEPR, that is also done. Third, valence bond theory. What was that? We did it, right? What is it? Hybridization. That is also done. We have understood the meaning of hybridization and we have seen that why hybridization is taking place. Now, the fourth topic related to the same thing is resonance. It's a very small topic, it's not difficult. You all already know the meaning of sigma and pi bonds. So we are ready for resonance. Now, what is resonance? Okay, children. I'm giving you CO3 2 minus. Can you draw the Lewis dot structure? Central element, carbon. In skeleton, I'm going to make 3 oxygens like this. I'm going to count the total valence electrons. How much? Like this. There is 2 minus. So what does it mean? That 2 of the oxygens are with 3 lone pairs And one of the oxygen is doubly bonded. You can see that carbon is not in trouble. It can make maximum 4. It is with 4. And now put the formal negative charge. This 2 minus. 1 is here. You can check the formal charge. 1 is here. 1 is here. If I say that this is oxygen 1, this is oxygen 2, this is oxygen 3. There are 3 oxygens. Now I'm teaching you resonance, children. Try to listen everything very carefully. Resonance is a big topic in organic chemistry, but for AP chemistry, we have to learn in a simpler way. There are 3 oxygens. But how did you select that which oxygen is going to have a double bond? How can I select? I cannot say that, oh, oxygen 1 is always holding the double bond. No. This pi bond is moving. It's not fixed. Like in structure 1, it is on oxygen 1. I can make another structure where the pi bond is on oxygen 2 here. Like this. This is oxygen 1, this is 2, and this is 3. So you can see the pi bond has come on oxygen 2. Right? These are resonating structures. The pi bond is moving. Only pi bonds and the sigma bonds can move. Oh, sorry. Only pi bonds and the lone pairs. During resonance, pi bonds, you know the meaning of pi bonds now, and lone pairs are moving. Do not touch sigma bonds. They are strong. You cannot break them. So don't touch them. What can you break? Pi bonds because they are sideways overlapping. Easy to break. Or you can move the lone pairs. Like here, earlier there were only 2 lone pairs on this oxygen. Now there are 3 lone pairs. And the pi bond is here. I can make another. What is the other structure, children? Can you draw the other one? Where is the pi bond now? Good, Siddharth. Where is the pi bond now? On oxygen 3. Yeah. This is the third one. This is oxygen 3 holding the pi bond. So this molecule has how many resonating structures? 3. These are interconvertible. Interconvertible. Structure 1, structure 2, structure 3. Can you see the double-headed arrow? This 2 can go to 3, 3 can go to 2, 2 can come to 1, 1 can go to 2, continuously moving, continuously. Okay, now let's do experiment. Now I'm performing an experiment, children. I have a electron microscope, a big microscope, which can take the picture of the electron cloud. When I took the picture of this carbonate, I found carbonate with all bonds exactly same. There is no double bond and there is no single bond. In fact, what I could see from the electron microscope, that all the bonds are partially doubly bonded. This is the real structure. And the negative charge, which I'm making here on this oxygen and on this oxygen, then I'm moving it to other oxygen, that is also not on any 2 oxygen. That is also all over on all the oxygens. It's like this. This is called as the real structure, the resonance hybrid. I use the word pi bonds and lone pairs are moving. I'm replacing this word by a much better word in chemistry, that the lone pairs and pi bonds are delocalized. Are delocalized. Delocalized means, localized means fixed. Delocalized means they can move here and there. I'm located here means I'm living here. But if I move from my location to some other place, I'm delocalized, right? So delocalized, English word. And this is the resonance hybrid, where each carbon is partially doubly bonded with the oxygens. And the lone pairs, which we were earlier making on one of the oxygen more than other oxygen less, now they are uniformly distributed all around it. So resonance means delocalization of pi bonds and lone pairs, and the molecule exists in the resonance hybrid. We are clear about it, children? Now the question can be like this. SO4 2 minus. So you draw the Lewis dot structure. We have already done it. There are 4 oxygen. 2 of the oxygens are with 3 lone pairs and a negative, like this. And 2 oxygens are doubly bonded. If I put these oxygens and 1, 2, 3, 4, can you tell me how many resonating structures I can draw? Like in this, the double bond is between 1 and 2, right? I can have a double bond between 3 and 4, isn't it? I can draw double bond between these two rather than 1 and 2. I can draw double bond between 1 and 4, correct? I can draw double bond between 2 and 3. I can draw double bond between 2 and 4. And I can draw a double bond between 1 and 3. So how many resonating structures? 1, 2, 3, 4, 5, 6. This is between 1 and 2. And they're interconvertible. Is it okay? You want me to draw, or you can draw it on your own? Shall I draw them? Like 3 and 4 means sulfur, and there is a double bond with oxygen 4 with 2 lone pairs, with oxygen 3 with 2 lone pairs, and the other 2 oxygens are singly bonded, 1 and 2. Like this. This is 3 and 4. 1 and 4, sulfur, the double bond is between 1 and 4 carbon. Like this. And other 2 oxygens are singly bonded, holding the negative charge, and so on. So this can be a question, draw the resonating structures. But what is the resonance hybrid, children? So when you see the molecule, this particular ion in a electron microscope, you will not see any double or single bond. What are you going to see? The hybrid of the resonance. And the hybrid of the resonance is that every oxygen is making a partial double bond with the oxygens. This is the resonance hybrid. This one. There is no double bond, there is no single bond. What is there? A partial double bond. Because the pi bond and lone pairs are delocalized on all oxygens. There are four oxygens, so they are delocalized on all four oxygens. Is it okay? Yes, children, ask your questions. Very good, Veer. Sanjeev, any questions? Because then my turn. Topic is done. Now we have to practice questions. Sanjeev, any question? No? Okay, Siddharth, Sashank, and Anish. Yuk, no questions? Okay, good. Ready? Then answer my question. Okay, Siddharth is playing safe. He's saying right now, no question. Okay, O3. Make the Lewis dot structure. Ozone, very popular AP chemistry question. Free response. Very popular. I think after every 3-4 years, this question is there. Exactly in the same manner with some twist in the language. That's it. Central element, oxygen, skeleton, oxygen, oxygen, total valence electrons 18. Complete the octet of this oxygen. What should I do? You can see there is no charge. What should I do? How many? A double bond with two lone pairs. Okay. Siddharth is saying, shall I make a double bond here also? Okay, Siddharth. Play safe. You're not playing safe. Okay, how many are used? How many are left? How many are used out of 18? Only 16. How many are left? 2. Where it will go? Who will hold these 2 electrons? Siddharth is saying put it on the oxygen. Can you check how many electrons are there on the central oxygen? Check how many you have placed in total. Do you think, Siddharth, oxygen can hold 10 electrons? It is in the second period. It cannot have more than 8. So we are very wrong. So if I make this as my structure, I'm left with 2 electrons which no oxygen is interested. Every oxygen is with 8. So where these 2 electrons will go? That is the reason this structure is wrong. So what is the structure then? Oxygen, one of the oxygen will make a double bond, but other oxygen will make a single bond. It cannot make a double bond because we have to accommodate these 2 electrons also. Now you place 3 lone pairs over here. Now you check how many are used, how many are left, and who can hold it. Now the central element can hold it. Very popular Lewis dot structure of O3. Ozone. Veer, can you check the formal charges on these oxygens? What's the formal charge on oxygen 1? This oxygen? Formal charge, children? Formal charge. No, Veer, you are wrong. Is the valence electrons minus number of bonds minus 2 times lone pairs. Yeah, it is 0. What's the formal charge on oxygen 2? Yes, all of you, please. Oxygen 2. Siddharth, Shashank, oxygen 2. 6 minus 3 minus 2 times 1. Why are you taking so much time? Plus 1. Yes, Yug, very good. Oxygen 3. Oxygen 3, you should know now without calculating. 6 minus 1 minus 2 times 3. What is oxygen 3? Minus 1. So this is the Lewis-Strauss structure of ozone. Can you draw the resonance? I made the double bond between 1 and 2. I can have the double bond between 2 and 3, isn't it? So let's make the resonance. The double bond is now, oxygen 1 is now singly bonded, oxygen 2 is now doubly bonded. 3 lone pairs here. Minus is here now. Central oxygen plus 1 is here. No change. And this oxygen, 0. This is the ozone molecule which has these two resonating structures. Let's draw before ending the class. Let's draw the resonance hybrid. This is the resonance hybrid. Because the double bond is moving, the pi bond is moving. This is the resonance hybrid of the O3. No charge. So the electron density is moving like this, delocalized like this. So none of the bond is double or single. Both of them are holding the central oxygen is holding these two oxygens with partial double bonds. So that's the topic of resonance, children. So we have done a great part of the unit 2. The next class will do the remaining part of the unit 2. I think we are left with very simple things now. So see you in the next class. If you have any questions, you can stay back. Bye. Bye, Veer. Bye.